This lecture segment finishes up our discussion of program or process memory space, looking at how its layout differs on different machines, and looking at holes in the virtual memory space. And we'll end with a little drill I like to call safe, risky, and dumb. So, starting here with the memory layout on different architectures. The text segment and data segment, BSS, RTS, runtime heap, all exist in any C program on any architecture. But their relative positions and the direction in which the RTS grows, upward in memory or downward, vary per architecture. I'm going to run the ProcSpace.c program, shown over here in the diagram, on my local machine, and I'll show the output. Thus, look closely at the code for ProcSpace.c and determine in which memory segment each variable or address resides. Be careful about the difference between the address of a pointer and the address of its target. From your analysis, answer the following questions. What are the relative positions of the text segment, data segment, BSS segment, RTS, and runtime heap on my local machine? Does the RTS grow up or down? What limits might there be on its growth? Is the BSS higher or lower in memory than the main data segment? So, coming back from what I would think would be a fairly considerable pause, and one in which I would hope you do a diagram of the memory layout, and please do that if you haven't. And then let's talk about the answer. First, the function addresses on line 17 here, and printed out up here, give a sample of text segment addresses. Looks like those addresses are in the 4.1 million range. And then the addresses of ALEC1 and ALEC2, not their content, their addresses, and the address of stir, are main stack frame addresses. So they mark the mains stack frame as being in the 2,665,500 range or so. And that's below the text segment. The text segment's higher up in memory. The address of flocal, which is, of course, in the call of F in a local 1 to F, marks its stack frame as in the same range, right there, but slightly lower than those of the main. So the RTS apparently grows downward in memory. And it can't very well grow below address 0, so it won't extend beyond 2.5 million bytes or so, perhaps less than that. Now, the locations of slocal 1, slocal 2, and global 1 are all in the data non-BSS segment, since they are initialized. And that appears to be above the text segment, and they're all adjacent to one another, starting at 4202, 496 for global 1, and then 500 and 504 for slocal 1 and slocal 2. Now, nearby is the location of the hello string at 4202, 574, and that would be along with other string constants as well, of course. Now, the locations of slocal 3 and global 2, all BSS residents, are about 4K above the other data segment variables at 4206, 592, right there, and 4206, 848, right there. So the BSS is above the initialized data. And then finally, the addresses in ALEC1 and ALEC2 are way up around 536 million, which is a long way from the rest of the data. And the two successive allocations are in increasing memory order, so that address is probably the start of the runtime heap. So, summarizing here then, we have first the RTS, draw a little diagram, growing downward in memory, and then the text segment, and then the data segment with BSS on top, meaning by that higher in memory, And then finally, way up at 536 million, the runtime heap. Okay, so here's the same program output run on another machine. Decipher this one in the same way, drawing a similar diagram. And coming back from a pause there, it looks like we start with the text segment, which is way up at address 134,513,000 or so. And then right above, later in memory, right above that is the data segment, which apparently starts with the string table and then the rest of the globals. Again, with the BSS data on top, higher in memory than that. Then we have the runtime heap, starting at 150 million or so. And finally, way up at 3.2 billion, the RTS growing downward. So I'll run that up here. It's not all to scale, of course. And going downward like that. Now, the arrangement of RTS and heap in this case is a little more conventional, with the RTS based at a very high address and growing downward toward the heap. Now, do you really need to know the exact memory layout of each process space? No, not for routine programming, but understanding the way it all works is critical to proper C programming even so. We'll see this in the exercise at the end of this segment. And seeing the huge memory gap between the RTS and runtime heap, especially in the second example, leads to an interesting discussion on virtual memory space. Now, as you know from earlier lectures, the MMU maps your program's zero-based memory addresses to real addresses that may be anywhere in memory. We speak of virtual addresses, the zero-based ones, and physical addresses, the real ones. And though your virtual addresses, assuming a 32-bit machine, can run from 0 to over 4 billion, the program doesn't actually get that much physical memory to use. Indeed, on an older machine, there may not even be that much physical memory. Instead, you get physical memory to support only part of your virtual addresses. And if you access outside of that, the result is a segmentation fault, as described in earlier lectures. But what we did not discuss earlier is that your allowed virtual space may have holes in it. Let's look back here at the second architecture with the RTS at about 3.2 billion and the runtime heap at about 150 million. Are there really 3 million bytes, or bytes of unused memory between the two? In terms of virtual addresses, yes, but the vast majority of that space is not mapped to physical memory, and if the program tried to use it, a segmentation fault would result. In a typical process space, the usable virtual addresses are not contiguous. If the RTS, or the runtime heap, runs out of mapped space, it's usually possible for a program to request that the operating system arrange for more virtual addresses to be mapped and thus usable, sort of filling in the hole and extending the area for the RTS or the heap. But unless this is needed, it's a waste of memory to map those unused virtual addresses to physical memory. And almost invariably there'll be some space between the two that is not mapped at all. And while we're at it, not all virtual addresses are writable. Almost all MMUs can be configured to map parts of a program's virtual address space to physical memory, but in read-only fashion. And so question 3, for which of the areas of the process space does read-only access make sense? There's one in particular that is almost always mapped read-only. And coming back from a pause there, the text segments contain code that should not be modified by the program and are almost always mapped read-only. Indeed, modifications to the code would probably result only from a wild pointer. It's certainly not something any program should do intentionally. And mapping the text segments this way opens up an even more interesting option. If several programs are running the same code, say for instance several instances of the same word processor running, then their text segments can all map to the same physical copy of the code. Sort of thus, with physical code drawn in here. I should say physical memory drawn in there. And the two text segments from presumably same program, different processes, mapping to the same physical memory location. Now, the RTS and the other data all have to be separate, but the two programs can share code. Okay, visualizing the layout of process space helps you decide whether certain C code patterns might end up accessing bad locations in memory. For instance, you already know not to follow a pointer to an allocated block that has been freed. Each of the following in-lecture questions presents a small C function. And for each, you should decide whether the function is safe, whether what it does is not likely to cause a memory access bug, or whether it's risky, it might cause a bug unless the caller clearly understands how to use the function, or if it's plain dumb, will pretty much automatically be a bug. So, question 4, let's start with the one here in the transcript. And trying something new for those who don't like looking at the transcript at the same time, let's just put it right in the diagram. Is this one here safe, risky, or dumb? And don't look at the answer, just pause and think about it for a minute. And coming back from a pause, the answer, as you can read in the fine print there, is this one's dumb. This is really a review from the RTS discussion. Loc becomes garbage upon return from F1, so F1 is returning the address of garbage data on the runtime stack. Worst still, loc will retain its old value until its area on the RTS is overwritten by a later call, so this is an unlucky bug. Okay, so what about this one? Let's just change it slightly and make it static. Coming back from a pause there. This one's safe. Loc being static, it now has a life beyond the current function call, and it's not on the RTS at all. Okay, well then, what about this one? Now I've got pointer pointing to an allocated block, and then we're just returning that. Coming back from a pause. This one's risky. The caller needs to know that it's getting back a pointer to an allocated block and thus has responsibility for freeing it, because F3 sure isn't going to be freeing it. By the way, if you thought that the block itself would be freed because pointer ceases to exist, that's not true. Allocated blocks are freed only by calling free. And then number 6, perhaps the most interesting of them. I've got a static int and apparently a parameter that's meant to point back to something in the caller, which I will set to 42. And I'm going to save the parameter as well in my data. So, coming back from a pause, that one's risky or dumb depending on your viewpoint. I'll say dumb personally. You're retaining a pointer in static storage to an entity that you have no idea will stick around. Maybe data is pointing to a local variable in the caller. That local will stick around while F4 runs and for a while after F4 returns to the caller, but once the caller returns, it'll cease to exist. And yet, the static variable will continue pointing to it. At the very least, the documentation for F4 must clearly state that one may only pass the address of permanent values like globals or other static locals. And a final note, examples like these make great test questions. Just saying.